Okay, hello, welcome everyone to the compiler's rating group. Today's paper is an implementation of Self, a dynamically typed object-oriented language based on prototypes by Craig Chambers, David Unga, and Elgin Lee. Further, there were some thanks given at the end of the paper to Randy Smith, one of the original designers of Self, Peter Deutsch, who was instrumental in many of the discussions and seminal ideas, and Beiwei Chong, for graphicals for a Self's graphical object browser and being a big contributor to the Self programming language. So this paper covers the Self programming language as described. It's kind of an interesting language. I think it's best to compare it to Smalltalk and the differences thereof. Smalltalk is an object-oriented language where everything is messages. It is a class-based object system where every object has a class and classes have meta-classes, etc., etc. Self is different in that it's a prototypical object system instead, meaning that instead of having a fixed class in which you're based on, you design your own behavior, right? There is no formal structure as there is in class-based object-oriented. To give you kind of a rundown of the language, I think it's probably useful for me to show you a bit of Smalltalk because the syntax is very similar and the differences in object orientation don't really show up in simple examples. So here you should be seeing my environment. I'm sorry, I can't really zoom it in. But the Self programming language is kind of like this, in which you have a class you have an object in which methods are defined on. So for example, the paper uses min as an example. So if I full screen this, we can see down here, sorry for the text being so small, min is defined taking a magnitude, and itself is the current object, is less than a magnitude, then the if branch goes off, otherwise the else branch goes off. And, words are kind of defined in this fashion, where you always have an object in which a method is being applied on. It makes it look almost forth-like in that, if you have a function like suck, which adds one number, it will be self, 1 plus, 1 plus, 1 plus, 1 plus, etc. And so the syntax is very similar to this. I just kind of bring this up because it's going to follow, this kind of style of programming. So just FYI, I just kind of wanted to get over this because this is like the language overview. Methods are applied on objects. You have a parent, which is who you derive from. And if the message doesn't hit you, it goes up the parent chain and the message tries to get applied on them. Right, that's typically how these work. So that's kind of like a rough overview of Self in very rough words. Some other interesting notes is that one thing in the paper that they make sure to emphasize is that Self has less primitives than Smalltalk. Smalltalk implementations often fix things like while do. They actually don't use the message passing system to do it for optimization reasons and leave that to the compiler, so you can't actually overload it, and they make a big deal of them not hand wiring low-level methods such as plus equals if true and all that. And so that's kind of what this section goes on about. Here's a pretty good idea of the object model which we're working on. So there exists some point trait which has parents, print, and plus with these definitions. And we may have two different kinds of points. We may have a Cartesian point and a polar point. And a Cartesian point would define things like x, y in their setters, and a polar point may make rho theta in their setters, for example. And that's what these are, where the parent of a Cartesian point is able to derive rho and theta. And so this is, if you implement in a naive way, kind of what this would look like in memory. Every time you make a new parent point, every time you make a Cartesian point, it has to copy all these things over. So a really interesting thing that the system does is implement a strategy called maps. It is folklore, at least I've seen on the Lisp Cafe channel on Libra, that any self-respecting JavaScript implementation will use this idea of maps. And Self is kind of the language that made this idea. And namely, if you didn't model this with maps, like our Cartesian example before, every time you make a new point, it has to be like, oh, I have a point and I have the setters. And this gets worse and worse as we add new methods on top of the Cartesian point. because while all these get cloned with every single object, meaning each allocation is quite ridiculous. However, they have this little strategy called maps, which works quite nicely, where a map is immutable. So right here, the Cartesian point map is immutable; it does not change. And so when we make a new point, we just copy the x and y, since they're mutable and they can change. What we do is we make a point and we just have the information for that. We don't even store that there's an x and y. We just have the mapping from the Cartesian point to its map, and then have this object right here, say the offsets within the object where they are. This means instead of wasting 2 words of allocation for x and y, and this can go up to n for every single method, it's just, you just waste 4 spaces, right? You waste 2 spaces for this, and then there's 2 allocations per object, which we'll get into a bit later. But this heavily reduces the allocation within the implementation, and make things quite efficient, because now we kind of can see that having immutable points means that we actually have less allocations per object, which was probably good for inline caches. So there's a lot of really cool tricks. There is some wasted stuff like this, where there's this Cartesian points trait which goes to its map, and there's nothing there. I think you could probably remove the indirection if you're smart about it. It depends on how some of the properties shake up later. But this is kind of, I think, the most important idea, is this idea of like maps, and being able to say, well, given a dynamic structure, we can optimize it without having to declare to the compiler that this thing's special. It just knows to optimize new objects and group them together based on the format. It's a very dynamic process. They talk about other things, like they have 2 memory regions, one for objects and one for bytes arenas. This should be familiar to anyone who's written a lot compilers, I guess, because I think it's fairly common these days to have 2 arenas, one for like a byte array pool and one for a not byte array pool. So that's kind of standard. But some other interesting things. So this language is fairly minimal, but what's really neat is that they use 2 bits for tagging information. 0, 0 is just an integer immediate. 0, 1 is a self-heap object, so meaning it's some object on the heap. 1, 0 is a floating point immediate, and then 1, 1 is a mark header word, which every object has. And here's the layouts, and this is why I said every object has 2 allocations plus how many immutable slots, because they have this thing called a mark, which is all the information needed for the garbage collector, and what other informations you need on the system. You have the map, which references the map, which we talked about a second ago. So this thing just points to a map. For a map, it points to the map. All of them point to the map. It's just a way of saying that this thing's a map if it points to the map. Like objects have like slot contexts. Object arrays have elements and all that. It's not too interesting. I guess for methods, you have your bytecode with it. And I will get more into how the bytecode kind of saves information throughout the systems. So sweet, we're finally getting here. Cool. So for example, we're going to go over the Cartesian point, and I'm going to go back to my Smalltalk implementation. So if we restore this to its proper size, and we go to the Cartesian point that I had laying around. Where did I have my Cartesian point? Yes, don't care. Sorry. I thought I had a Cartesian point. No big deal. Oh, here it is. So a point is really basic in what we saw before. And it has 2 mutable slots, x and y. And these x and y can be set. But everything else about them is, fairly basic. It has a parent and a few other things. But most importantly, it has 2 mutable slots. So what the compiler does is that when we model it in memory, we just have the mark, we have the map, and we have the 2 slots with the offsets. And in memory, the Cartesian point object itself, like the map of it, is fairly basic. It has the object length, which is 4. In this case, it has 5 slots because they have parent, x, y, and the 2 setters. That's 5 things. And the parent goes to the parent, so that's all nice and dandy, and these just reference in the slot. So in higher detail on how the memory lays out for mutable and immutable data, this is really good at laying that out, right? Where X is this assignment slot, X is the data slot, and it's saying it's offset 2 within this map. So right 0, 1, 2, and then Y should be 3. Yeah, 0, 1, 2, 3. So this format is really compact. That's basically what this is showing you. The entire Cartesian point fits into 4n plus 33 words for its family. So every time you allocate a new object, it's another 4 words of allocation. 2 words, again, for the map and the mark. Yeah, it's fairly basic. Something else that's really interesting about this language is that its bytecode is very basic. It's a very, very simple bytecode, yet it expresses so much. I believe it's on par expressiveness with Smalltalk, which is a very expressive language without much sugar. And Smalltalk has a lot more primitives. For example, all the primitives there are self, pushing yourself onto the stack, a literal, so you're pushing some literal onto the stack, a send a message, so you're sending some message, a self send, where you're sending a message to yourself, a super send, where you're sending a message to your parent, delegate, which you're delegating a message to the parent, non-local return, so this handles things like return and see, long jump, set jump, all that good stuff is done by a non-local return and index extension. Because what's really interesting is that since there's 9 of these primitives, this fits within 3 bits. So what they do is that they encode it in a single word, which is 3 bits for the instruction and then 5 bits for the index. And so this index extension means that we can access more than 32 words. There are 32 slots, because you can imagine that if you have a really big Cartesian point, there may be hundreds of slots, because maybe programmers have defined new methods for it, like equality, greater than, less than. You can list off a bunch of functions and it won't fit in 5 bits. So, there's this thing called index extension, which prefixes the index. It just prepends it. And so an example that they give is a print example, and here's like what the method would really look like. Methods are kind of compiled in 2 parts: a literal array and its bytecode array. This should seem familiar to compiler developers here, because in a compiler you usually have a bunch of fixed numbers which you reference from some type of data pool, right? You can reference your literal pool, and it's fairly quick. So in this case, self is 6, and they want the 0th item on it. So 6, 0 is X, because the literal element X is 0. Then they send the message 1, print. So if you see here, print is here, and then 4 is send. So they're sending print. Literal is 2, and then this 2 is in the object pool here. We print again. We push through Y with 3, and then we print again. So this is an example of the bytecode interaction. Something I guess interesting to note is that although this is a bytecode, they evaluate this to native code before execution. They use the Deutsch, I have to look up, the Deutsch Schwitzerman translator from Smalltalk 80 is what they base this on. And what it does is compile this to native code before it's used. So although we're talking about bytecode, in reality this gets executed as a native code. And so this is kind of the bytecode. This is the entire bytecode. This is everything, which is really nice. It's a very minimal thing. Unlike Smalltalk, which has a lot more primitives, which this paper mentions that specifically Smalltalk's bytecode representation is to make programs shorter and more efficient by doing so. This self compiler that they give here is 2 times faster than any Smalltalk implementation was at the time. I guess looking into the future from when this paper was made, this ended up going into Java Hotspot. So I think Oracle, I think it was Oracle at the time, or Sun. I guess we'll call them Sun. Sun bought out the Smalltalk people, and they kind of used them in the implementation of JVM Hotspot. I believe they just took the self-implementation and took a lot of the ideas and used that for compilation. So, their compilation techniques were quite nice. They mention all that here. They fix no primitives. Everything is wonderful. Next, they talk about chapter 5, which is the compiler. I want to kind of get into the compilation. They're going to be covering the program min. Min is a really basic program. If the object on top of the stack is less than the argument, if that's true, then you return self. Otherwise, on the false branch, you return the argument. Right? This would be min, right? Is 3 less than 5? Well, then return 3. Otherwise, return 5. Where 3 is the object that, is the self object in this case. And so when you look at the flow graph, it kind of looks like this, right? You have push self, push arg, you send greater than, less than, sorry. You then push self, create closure, and now you can say if true, false, else, because, well, you have all the objects you need on the stack. You have the self object, which would be the result of the send great less than, and then you have the true branch and the false branch, which are closures, because you need to capture these arguments. So this is kind of what this looks like. This is rather inefficient. The problem with a Smalltalk system is that things are largely polymorphic. Some things are actually mega polymorphic, I believe, is what Gillard Branca, I believe that's his name, states in one of his blog posts that I believe the Smalltalk 80 paper found. And I believe we read that paper as the first compiler reading group's paper. So 8% are mega polymorphic. I want to say 20% are polymorphic, and like 80% are we know the call sites. However, if you're just looking at this method, you don't know if this is on floats, on ints. You actually don't know what this is on. And that's really bad because, well, you have to do this logic every time. You can't just short code greater than, right? Like this logic can boil down quite a bit. However, since we know what class this is implemented on, for example, if I go back to my Smalltalk implementation, some things are quite interesting. Close this. Yes, I don't care about saving my changes, thank you. And I look at min, so 3 min 4. I want to look at all the uses of it. Sorry, that's the wrong one. Thank you. So there's a lot of different things that have min, right? Character block has min, ICE extension job has min. All these have some type of min in it, which is really annoying. The one that we want is magnitude. So magnitude is this one. In the self system, they actually have an implementation on integer, which is quite efficient. And I can show you that implementation, but you can see that like the one min, if you're looking at the traditional Deutsch-Schifferman translator from Smalltalk 80, would just compile min once. For every single min, there's just one min method. However, this compiler is a bit smarter. When it sees the definition on integer, it knows the type of self. And this is without any type declaration, it's able to optimize it. And they give the definition for less than on integer, it's int lt prim arg if false. This if false is there if it's not of the right type. So this is kind of like a fail case for if the thing is not of the right type, it's probably past type checking, or maybe it hasn't, and it's just the wrong thing. It needs some fail logic. So this is that. And what's cool is that it has message inlining. You see something very similar with Haskell's type classes. I guess Rust traits, I think those things inline. Generics don't inline, but type classes in Haskell and ML tend to. This is very similar. And you can see here it looks like this. The send less than then gets transformed into push, create, closure, call. The things in bold are more expensive. So, send is expensive, create, closure, and send are expensive. Here, we have more expensive things, create, closure, and call. So the great thing is that we've inlined this. Great. We don't have to do a message lookup to figure out, oh, hey, which less than should we dispatch to? Should we dispatch to the integer one? So instead of doing it at runtime, we do it at compile time. Excellent. However, this is not enough. This is still expensive, right? There's still a bunch of stuff where I'm calling it, and then, if this is true, then we push. So what they also have is primitive inlining. This is very similar to const as expressions from, I think, certain scheme compilers have it. Quite powerful. Factor has this in their own constant folding expression, and this is also known as constant propagation. That's like a weaker version of this, and they get into some of that a bit later. For that, they inline the int lt prim. So this gets inlined to its assembly. And this is kind of what it looks like. So this thing checks if the thing is an integer. If it's not an integer, then we push the fail logic, we create the closure, and then send the value. However, if it is an integer, we compare it. We use the comparison of the arg to self. If it's less than, we push true. Otherwise, we push false. Which is quite good. Now, if we're looking at things, because the next message to be evaluated is send if true false. So if we kind of continue with this logic and inline if true false, because that's what would be inline next, we get a tree like this, where we get and argbt b0 push true. But you notice this: if true false, we're pushing true, push self, creating closures. But we know, for example, if we're pushing true, so what would happen here is that we message split. So instead of splitting once and joining here in this subtree, we're just saying for each of these branches, create the subtree. So copy this into each subtree. It does this by message inlining, like I mentioned earlier. Well, I guess I didn't mention it. This compiler is smart. Unlike compiling one min method for everything, it compiles one min method per concrete object. So in this case, true, false, and values are all different versions, and so they call this message splitting, as you can see up there. And so it branches them like this. So now we know that the object coming in to send if true is true. For this one, it's false, and for this one, it's some weird values nonsense. And so we look up the definition. For the true object, if true, false, just returns true. So if you look at this, all this is saying for the true object, if true, true block, false block is equal to the true block, right? Since this is being compiled on true, it just returns the true block, right? Because, well, true is true, like this false block is dead code. So we just return the true block. And same with the false block, we do it with the false. So what we can now do is, well, we see this, we take this here, and now, boom, we just push self, push arg, because all that evaluates to the true block and the false block, which is self and arg, and all this code can go away. So now we've inlined it to all we already have to do is we compare self with the arg, push true, push arg. Instead of having to do a dispatch for less than and then doing another dispatch for if true less than, it's bam, it's done, right? Where this is still heavy. Now, a big issue comes up where what if these are big? Because when we talk about inlining, we don't want to inline big methods, and because that'd be quite horrible. Even GHC, there's a paper writing called the GHC inliner, or the dark secrets of the GHC inliner. They have a lot of heuristics about sizes and other parameters in order to determine what to inline. So this next state of questioning goes into that, and they call this type prediction. So if like one side is too big to inline, it knows something. It knows something about the logic. If true, if true, false, actually knows something about normal call patterns. Because of this, what it can do is compare the thing with true and compare the thing with false, right? So if it doesn't know anything about it, it knows that it wants to deal with the true or false just by the usage and what type of methods are around. And so it can generate out these two little checks dynamically. And so even if you don't inline everything, it's still able to check the objects coming in with true and false and split on the branches that way. And after we get to compilation, we end up with a call graph like this, where we check if it's like an integer. If not, we do our normal check, which we've inlined before, where if it's less than, we push self. If it's greater than, we push arg. For the unknown branch where it's not, it still does a comparison against true and false, just to make sure before doing these, and then it goes through its more complicated logic, because it actually can't figure it out. What's really neat is that instead of treating it like labels, it's kind of like a sea of nodes. You can see that this is a graph where these things point down. I think it's still a DAG. Yeah, this is still a DAG, I believe. But you can imagine this as a sea of nodes if the compiler were a bit smarter. But yeah, no, this is a really interesting compilation. And what they found was that this is 2 times faster than any Smalltalk implementation, even Smalltalk implementations which used explicit type annotations. Because the system knows enough information about the things it's being called on, it's able to remove polymorphic calls with non-polymorphic calls. Because of that, it's able to optimize a whole hell of a lot. If you compare this graph to the previous one where it has to do lookup, like with the create closure, send if true, this is expensive, right? Whereas this is very cheap. Unless if it's not an integer, this is very, very, very cheap. And if you know more information, it can inline even more. So if you could imagine augmenting this with further type information, you can get quite good. They mentioned this in the further section where they only really do this on the self object, but you could also imagine maybe doing it on the other arguments of the object as well, meaning that you can get some nicer optimizations. So that's like the rough compiler. However, that's not enough because this is supposed to be a realistic programming environment, or aims to be one. It must support a good programming environment and a good debugger and fast recompilation times. Otherwise, it's not a real environment that people care about, especially from the Smalltalk community. And so this thing has really nice technique called a dependency link, where essentially every time you compile a method, it checks in multiple points when methods are invalidated. So here's an example. So for the min method, all these are points in which this min method is invalidated. If the min method changes, well then I'm sorry, this min method is invalidated. If the parent like changes, like maybe the parent implements min, then this would be the correct min, I believe, in some circumstances. Therefore, this is invalidated. If less than is changed, this is invalidated because, well, the definition of less than changed and we've already inlined it. That's quite bad because, well, it'd be semantically incorrect and you'd be having dead code still living. So that's a horrible thing. Further, if the integer map changed, so maybe integer implemented its own less than or min, then, well, if we added those, this would also be invalidated. If true changed, then the definition if true false would invalidate this. If false changed, same thing, right? So what we have is this two-way mapping where if any of these change, we can invalidate the min method and flag it for recompilation. Factor tried not doing this. Factor used to have a system where it would keep the dead code alive, but that ended up in dead code showing up. And what they, I think, eventually settled on, and I think from the blog post from about 2009, I want to say, is that they ended up doing the selective invalidation. The reason why you want to do invalidation selection and not recompilation is because it would take too long. Because anytime you change this definition, suddenly you have to change a lot of your system if it's deep down. I believe, Ray, forgive me, I believe Hoon would just recompile everything on the spot. And if it errors, just toss it, essentially. Am I correct, Ray?
Yeah. So it has a sense of dependency links. It would recompile everything that's related to what you changed, or rather everything that's downstream of it. And yeah, if there's a compilation error, then your edit is just rejected.
Yeah. So other system handle in different ways. Factor just selectively invalidates it and basically checks it for recompilation later. It checks the stack effect and warns you that it's bad. But part of the impetus is that you want your system to be live always. Where when you do a change, it should happen in a fraction of a second. You know, when I redefine less than, it should not freeze my system for a full minute on recompiling everything. It should just be done, and that's that. And so they do that. They mentioned in the I think chapter 8 maybe doing what Hoon did, but they didn't get to it. Factor tried it and they had bad results in their case. But I'd say Hoon has a different use case than Factor in that instance, just by its very model. Either way, all these invalidate it, so this makes keeping a system live quite easier. These are kind of conditions. There's these 4 ways, and that's where we get these is through those 4 rules. Just 4 rules. If further things is that with all the inlining, this would be quite bad for debugging. Why? Well, the programmer has an idea on how messages work, right? When I send the min method, I know roughly what's being executed. I have a cost model of what's happening, right? The compiler optimizing it is wonderful. It's a great gain, but that's not part of the cost model, right? I know that I'm sending a self message. I know that these messages are being sent. So what happens is that it can reconstruct the call stack, right? I don't know if it can produce you both the efficient call stack and the naive call stack. I think it can with the information, but it's able to reconstruct the naive call stack by simply keeping source level debugging information around. So they keep the original. I think they keep the original definition stored in memory, and they keep the bytecode and enough information. When it does an inline optimization, it notes it, I believe. And so when a bug happens in the system, it's able to give you a stack trace as if it did no optimizations. This is quite useful because, like, semantically, that's kind of what you wrote and what you expect from a backtrace. Right, you don't really expect all the optimizations. I'm sure you can probably toggle it if they put in the effort. But it's really important because without a debugger, things are kind of foobarred when you're making a real system, right? Like, there's a reason why real Smalltalk systems have really good debugging capabilities. What I presented in the first reading group on the 20 years of Smalltalk, they've extended their debugger so they're able to even reproduce bugs on the VM level and debug it as if it were normal Smalltalk programs. It's that useful in your program to have. So, they put a lot of effort in this case on putting it. I highly recommend reading chapter 6. I'm kind of just skimming past it, but there's a lot of really great ideas here for making a live programming environment. It deals a lot with invalidation, making sure things are supported, and making sure that things are transparent to the programmer, which is a very important thing. They mentioned before that they don't have they have all the infrastructure, but I believe they don't have placing a break at a certain point working without, I think, recompilation, which is kind of sad, but I think they're just getting around to it. Some interesting notes on performance. This is actually quite a big project. This is 33,000 lines of C++, which to me is like 10, which is 3 times too many. For example, Factor was about 9,000 lines of C and then ported over to C++ later. So 33,000 lines of C++ is quite a bit, and 1,000 lines of assembly. I don't know how complicated it was, but they do mention that they had to compile down to a Sun 3 and a Sun 4, right? And then they have 9,000 lines of self code. Still quite amazing. They have some benchmark here. One issue that they had was that this took 7 seconds to compile. That may not seem like a lot, but it really is slow when you have a live programming environment. You usually want your code to load like immediately. I'm sure on a modern system, this would be compiled in less than a fraction of a second. But I believe there's like 900 lines that they mentioned, and it took about 7 seconds, which is a bit slow. That's how much they cared about, I guess, uptime of like programming your system. They got performance which was 2x of any Smalltalk implementation on the market, and about on par with some of the more typed ones. I believe it was on par, not with Strongtalk, but they mentioned another system here in which it was on par of. They had a lot of type declarations and maybe some restrictions on how some of the dynamicism works. They talk a bit about like the second generation machine and how they can make it even faster. I don't think their work kind of became a thing other than Java. There's some more other small South papers that I have, but I don't think they defined another self system with those optimizations that they wanted. Kind of sad, but I think all their work went into Java, much like how I believe Dan Ingalls did the bulk of Java implementation at some point. And Dan Ingalls was the creator of Smalltalk. Well, he created it with not Joe Armstrong, Alan Kay. Yeah, with Alan Kay, I believe. He was the main implementations guy. And that's roughly the paper. It's pretty good read. I recommend everyone to like read through it themselves. Does anyone have any questions? Did I skim over something? I guess one last note is that Smalltalk systems were 10 times slower than C, and this only brought it up 4 to 5 times slower than C. So a lot of performance gains still need to be had, and they were had later in Java, because Java is, fast these days, and a lot of that is thanks to the brave work that people like Craig Chambers, David Unger, and Elgin Lee did here in the Self paper.
Yeah, it does seem like most of the gains come from uh, reducing the cost of dynamic dispatch with a lot of aggressive inlining and so on.
Yeah, that was the majority of like the performance gains. I guess what's interesting is that their performance gains gave them their aggressive inlining was on par with them handwriting plus equals and if true, which they argued made Smalltalk less of a true system because it's imperative subset since you can't extend it. So yeah, pretty much all the performance gains came from that. I think the main takeaway for me at least was the map idea because I believe somewhere. I think it was maybe on Lisp Cafe on Libra. Um, the people who implemented the system didn't realize how hard it was to make an efficient self system, and this map idea really does save memory. This is more of a memory savings by quite a bit than a speed savings, but I think this is also a pretty nice win given how unstructured prototypical OO is in how it's done. So I think that's also quite an impressive memory gain. But yeah, that doesn't really bear out in speed other than like probably cache lines. Did they even have like L1, L2 cache back then to even measure? Because they don't mention any like cache gains, even though they obviously would here, like if they made big examples.
Yeah, I mean that was less of the bottleneck. Like in in the current day, that's using cache efficiently and vectorizing things is the performance bottleneck that's most important to get around. It wasn't so much then.
Yeah, that makes sense. Yeah, I don't know much about the Sun 3 or the Sun 4. I guess what's interesting is that they didn't run this on a small talk system on like they made special hardware for small talk, much like Lisp machines at Xerox PARC. They had the small talk machines. I believe they call them the D machines. And this, they don't think they ran this on the D machines. This was, I think, priority by the time that they failed. And so you're trying to do it on Stark hardware because this is '89 at Oopsla. So I think those systems have already died or are dying at the moment by the time this paper came out.
Yeah, I mean what's happened now is that uh, execution is so fast that data access really becomes the bottleneck in a huge way. Uh, Not that it's not so much that it wasn't in the past, but execution was actually slow enough for it to not be the single most important thing. And vectorization and vector instructions didn't exist as much.
Makes sense. What do you think about the object representation? Because one issue that I think is kind of apparent is that whenever you make a Cartesian point, it takes up 4 words. If you look here, you have the mark, the map, and the slot contents, meaning you're wasting 2 words of allocation. Meaning that if you're trying to put this in cache, half the space for this object is just wasted, right, on the mark and the map. Every time you do a new allocation, it's 4 words, and 2 of them are a waste.
Yeah, I mean you're spending it for flexibility.
That is true. I think nowadays you can probably cut it somehow if you're smart. I don't know how you would cut it, but I'm sure there's probably a way of cheating it. Um, yeah, I guess through another layer of indirection somehow, but you still would be, you know, charging a single word, which would suck. I'm not quite sure.
Yeah,
Other than maybe you tag the object in a certain way. and so you use some more tag bits because now we're kind of blessed in that we have what pointers are 48 bits rather
Yeah,
than
if you move to a 64-bit implementation, you have a lot more space for tag bits. Yeah, only 48 bits are ever used for address on current 64-bit CPUs, and that doesn't appear to be changing anytime in the near future. I mean, 48 bits is a lot of virtual memory to address.
yeah. So I think you can pull some interesting techniques in a modern system. There's some other papers from Self that we can look at in Smalltalk, but I think kind of gets its point across. I think how it models a lot of its code is quite interesting. How it has this nice bytecode that's really basic. Like anyone can implement these. I think um, with it took them 33,000 lines of code, I guess, but I don't know what all they implemented, like the entire environment or what they do in the C++. It seems quite excessive, in my opinion. But it looks
It's
like there's just some primitives.
probably mostly like the the compiler pipeline for going through bytecode and then to the native code.
That could
So
definitely be.
they definitely don't call out to things like some kind of LLVM backend, which didn't exist yet, as their backend.
Yeah, that's true. But I'm just trying to think because, like, I know that the Smalltalk guys got their system up quite fast, so I'm just kind of interested in saying because they also implemented it for a Sun 3 and a Sun 4, so there's probably some code there for like the different operating systems and like
Yeah,
issues there. But again, I think this bytecode is really impressive, especially if you compare it to Smalltalk. Like here on my Smalltalk system, I actually have an example for you. I believe if I look at the integer method for factorial, I want to inspect it. I don't want to print it. There it is. You have the source code here that's stored in memory. You have the bytecode like before, but the bytecode here is interesting. There's like pop into temp, there's send, there's jump false, there's like push constant. There's a bunch more stuff in this, like full closure, send closure. There's just a bunch of nonsense in there. Whereas if you compare it to the South, there's only like 9 primitives, and the IR of this is more complicated as well, right? So they managed to pull off a lot in a very small amount of time. The AST here is not too interesting, but again, it's mostly the bytecode here being not so simple in comparison to this. It's really elegant, I think. Because this pretty much defines any type of computation you'd want to do, which is quite nice. There's some
yeah. And
closures.
if you're 64-bit, you could maybe make it larger and not have index extension. I'm not sure.
I think you'd still want an index extension because, well, what you have a 64-bit word, you have let's say 3 of these, so then you have 60. I guess actually you don't need it because 62 bits is more than enough to represent any item on type of thing because what that's like trillions of methods on top of one object, which is not going to happen.
Mm.
So I think you'd run out of memory by that point. So I think you're right. Well, I guess they do this on a byte, right? They do this per byte actually, because
Yeah,
each is their byte. So I don't know, because they do a 5-bit object index with a 3-bit opcode. Um, yeah, it's hard to say really. Um,
yeah. I was thinking like if you did 16-bit words or something, but I'm not sure. You might end up still wanting it.
yeah, perhaps. Um, yeah, that's the paper. There's not much else to it other than inlining saves the day, and it was able to. I think what's important also to take away is that even if your language is highly dynamic and seems really hard to compile and optimize, there are tricks and you can make it fast. I think one of the leading developments for a lot of compiler techniques were kind of these dynamic languages, because being slow is not all that acceptable when you're waiting on the system. And so they had to pioneer a lot of interesting techniques to make things faster. And this I believe is one of those interesting techniques that kind of came out of it and got merged into a more static language known as Java. Yeah. Okay. Nice. With that, I will stop the recording.